Right then, have you ever gazed up at the sun and thought, that's a lot of energy going to waste? Imagine for a moment if we humans could tap into that cosmic powerhouse directly. What if our skin could do what leaves do every single day? What if we could photosynthesize? This isn't just some far-fetched science fiction idea, it's a question that could completely rewrite the rulebook for space exploration. Forget packing freeze-dried ice cream and mountains of food pouches. The new frontier wouldn't just be about where we go, but what we become to get there. It would be the single greatest leap for humankind since we first harnessed fire. A biological revolution that turns every single astronaut into a walking, talking, solar-powered generator. The very concept of a space mission is built around logistics, and the biggest headache is always mass. Every kilogram you launch into orbit costs a fortune, and a huge chunk of that weight is food, water, and oxygen. Now picture this. Astronauts with genetically engineered, chlorophyll-infused skin. Suddenly, the most fundamental limitation of long-duration space travel begins to melt away. These new humans, let's call them Homo sapiens solaris, could bask in the unfiltered, glorious sunlight of space and create their own energy. This isn't just about saving on grocery bills. It's about unlocking the ability to travel further, stay longer, and build permanent homes among the stars, all powered by the nearest star. It's a game-changer of galactic proportions. This single biological upgrade would send ripples through every aspect of space travel. So what exactly is this photosynthesis business? Put simply, it's the most brilliant chemical recipe on planet Earth. Plants, algae, and some clever bacteria have been doing it for billions of years. They take three basic ingredients: sunlight, water, and carbon dioxide. Inside their cells are tiny green factories called chloroplasts, which contain a magical molecule called chlorophyll. That's what makes plants green. This chlorophyll grabs the energy from sunlight and uses it to smash apart water molecules and combine them with carbon dioxide. The result? They make glucose, which is a type of sugar, their food. And as a handy little byproduct, they release oxygen. It's the ultimate solar-powered, self-replicating, life-sustaining chemical reaction. Now imagine we could get in on this action. Our human cells are already amazing little powerhouses, but they run on the food we eat. If we could integrate chloroplasts into our skin cells, we could have it both ways. We could still enjoy a good meal, but our skin would be constantly trickling energy into our bloodstream. It would be like having a solar panel woven directly into our biological fabric, a silent, efficient, and constant source of fuel. Of course, it's not quite that simple. Human skin is very different from a leaf, so a bit of genetic tinkering would be in order. We'd need to make our skin more receptive to light, perhaps by making the outer layers more transparent. And we'd need to get those little chloroplasts to feel right at home inside our cells, working happily alongside our existing cellular machinery without causing any trouble. It's a huge biological ask, but in our thought experiment, our brilliant future scientists have cracked it. So the system would work like this. Our solar-powered astronaut breathes in the carbon dioxide from the recycled air on the spaceship. They drink water. They expose their skin to sunlight. The chloroplasts in their skin get to work, cooking up glucose. This sugar is then absorbed directly into the bloodstream, providing a steady supply of energy to power their muscles, their brain, and everything else. As a bonus, their skin would also release a small amount of oxygen, contributing to the breathable atmosphere inside the ship. It's a beautifully elegant, closed-loop system, turning the astronaut into a vital part of the ship's life support system. The single biggest advantage of photosynthesizing in space is the massive reduction in launch weight. Think about it. A typical astronaut on the International Space Station needs about 1.8 kilograms of food and packaging per day. For a 3-year mission to Mars with a crew of 6, you're looking at nearly 12,000 kilograms of just food. That's the weight of 2 large elephants you have to blast into space. This colossal mass requires more fuel, a bigger rocket, and a much higher budget. Now, enter our Homo sapiens solaris. If photosynthesis could provide even half of their daily caloric needs, the amount of food they'd need to pack would be slashed dramatically. Suddenly, that mission to Mars looks a whole lot more feasible. A mission to the asteroid belt, to the moons of Jupiter. These destinations, currently the stuff of dreams, creep closer to reality. The energy source is already there, streaming through space for free. All we need to do is catch it. This reduction in food supplies doesn't just save weight, it also frees up an enormous amount of precious limited space inside the spacecraft for more scientific equipment, better living quarters, or extra radiation shielding. Furthermore, this solves the problem of food degradation. Over long missions, vitamins in prepackaged food break down, and the taste and texture can become monotonous, leading to what astronauts call menu fatigue. A photosynthesizing astronaut, however, gets a constant fresh supply of pure energy. Food would become less about basic survival and more about nutrition and enjoyment. The psychological boost of not having to ration every last crumb would be immense. The energy independence is another massive win. Space missions are incredibly energy hungry. Solar panels on the outside of the ship power the computers, life support, and experiments. But here, the astronauts themselves become part of the energy solution. Instead of consuming resources, they are actively generating them. The oxygen they produce through their skin would reduce the load on the life support systems, which have to scrub carbon dioxide and generate oxygen. This creates a more resilient, self-sustaining ecosystem within the ship. The daily routine of a photosynthesizing astronaut would be fundamentally different from today's spacefarers. The day would likely start with a period of sunbasking. Instead of heading straight for a breakfast pouch, crew members would gather in the ship's observatory or a specially designed sun-soaking lounge. Here, they would expose as much of their skin as possible to the raw, unfiltered sunlight, perhaps performing light exercises or meditating as their cells topped up their energy reserves for the day. This morning ritual would be a quiet, communal experience, a moment to connect with the star that sustains them, replacing the hustle of a morning meal with a serene cellular refueling session. Throughout the workday, mission tasks would be planned around sunlight exposure. Extravehicular activities or spacewalks would be scheduled for periods of maximum solar illumination. An astronaut repairing a satellite would be simultaneously absorbing energy, making them more efficient and able to work for longer periods without needing to return for sustenance. Inside the ship, tasks in darker, shielded modules would need to be balanced with time spent in well-lit areas. The ship's lighting system would also be crucial, likely using specific wavelengths of light that are optimal for photosynthesis. The concept of mealtime would be transformed. While some food would still be consumed for specific nutrients, minerals, and sheer pleasure, the big, calorie-focused meals would be a thing of the past. Lunch might simply be a 15-minute break in a sun-drenched corridor. Socially, this could be a major shift. The ancient human tradition of gathering to share a meal might evolve. Perhaps the new social hub would be the hydroponics bay. Or perhaps the communal sunbasking sessions would foster a new kind of silent, shared bond. Personal time and sleep schedules would also adapt. Astronauts might find they need less sleep if their bodies aren't spending as much energy on digestion and are receiving a constant energy trickle. An astronaut feeling a bit low on energy wouldn't reach for a coffee or an energy bar. They might instead prescribe themselves an extra hour of light therapy. The entire rhythm of life in space would become intrinsically linked to the light of the sun. The iconic, bulky white spacesuit would need a radical redesign for our green-skinned astronauts. Today's extravehicular mobility unit, or EMU, is essentially a personal spaceship designed to protect its occupant from the vacuum, temperature extremes, and radiation of space. For a photosynthesizing human, it would need to do all that and more. It would need to let the sunshine in. The outer layers, instead of being opaque and highly reflective, would need to be largely transparent, at least across the torso and limbs, acting like a personal greenhouse. This clear material would still need to block harmful radiation like UVC and X-rays, but it would have to let the visible light spectrum pass through to the skin. This presents a huge engineering challenge. The suit would need a sophisticated system of filters, and perhaps even photochromic layers that could darken automatically in the event of a solar flare, protecting the astronaut from a sudden dangerous blast of radiation. The cooling system would also need a major upgrade. A person photosynthesizing is absorbing a lot of solar energy, and while some is converted to chemical energy, much of it will become heat. The helmet design would also change. Imagine tiny fiber-optic filaments woven into the fabric of the suit, collecting sunlight from a wider area and directing it onto the skin's surface. This new suit, let's call it a photosynthetic habitation unit, or PHU, would offer incredible EVA endurance. Today's spacewalks are limited by the oxygen supply and battery power in the suit, typically lasting around 7 hours. A photosynthesizing astronaut would be constantly replenishing their own energy and contributing to their own oxygen supply. Spacewalks could last much longer, perhaps for an entire 12-hour work shift, making construction and exploration projects on the Moon or Mars far more efficient. The suit becomes less of a survival bubble and more of an energy-enhancing exosuit, a symbiotic partner in the exploration of the cosmos. Just as the spacesuit needs a rethink, so does the spaceship. Current spacecraft design is really a story of compromise between crew space, scientific equipment, and massive storage for consumables. But with photosynthesizing crews, architects could start dreaming up ships that are not just a means of transport, but truly integrated ecosystems. The most striking new feature would be what's called the solarium or basking dome. This would be a massive transparent cupola, probably the social and psychological heart of the ship, made from advanced radiation shielding glass. Here the crew would spend a lot of time soaking up sunlight while exercising, working on laptops, or just relaxing and enjoying the view. Inside, the ship would be organized by light. Daylight zones would be filled with either natural sunlight or full-spectrum artificial light, all designed for active work and photosynthesis. Then you'd have twilight zones with softer ambient lighting for relaxation and socializing, where generating energy isn't the main goal. And finally, night zones, like sleeping quarters, would be kept dark. The ship's exterior could have a double purpose too. Imagine these vast sail-like structures, not for propulsion like a solar sail, but as giant lenses or mirrors. These light sails could unfurl to capture sunlight from a huge area and focus it, channeling it through fiber optic cables to the ship's interior. In the end, the ship stops being just a machine that keeps humans alive. It becomes a true symbiotic partner, a vessel where biology and technology work hand in hand to create a tiny mobile biosphere hurtling through the void. The health benefits for our solar-powered humans could be pretty substantial. A constant supply of glucose could lead to incredibly stable blood sugar levels, almost eliminating energy slumps, and maybe even reducing the risk of metabolic disorders like diabetes. Plus, the continuous production of oxygen at the cellular level might boost cognitive function, physical endurance, and the body's ability to repair itself. But yeah, this superpower wouldn't come without its risks. The most obvious danger is radiation. To photosynthesize, your skin needs to be exposed to sunlight, but space sunlight is packed with dangerous high-energy particles and radiation that can cause cancer or radiation sickness. So, those transparent suits and windows would have to be absolute marvels of material science, filtering out 100% of the harmful rays while letting the useful ones through. There's also the internal biological risk of oxidative stress. Photosynthesis produces oxygen, and while oxygen is essential, in its highly reactive forms it can actually damage cells. This could cause premature aging, cellular damage, and who knows what other medical issues. Astronauts would probably need to take a powerful mix of antioxidant supplements to protect their bodies from their own metabolism. And then, what happens when they come back to Earth, where the sunlight is filtered and weaker? They might feel tired all the time, or their engineered skin might react in strange, unpredictable ways. Finally, there's the simple, practical issue of energy balance. What if you get too much energy? Could an astronaut become overcharged? On the flip side, during a long period of darkness, they could run out of energy fast. The introduction of photosynthesis would really shake up the social and psychological landscape of a space crew. The shared ritual of sunbasking could become a key part of team bonding. But, this shared biology could also bring new social hierarchies or tensions. What if some people are just naturally better photosynthesizers than others? That could lead to an energy gap, where some crew members are always lively and full of energy, while others are struggling to get enough charge. This might cause resentment or feelings of inadequacy. Team dynamics during an emergency would shift too. In a power-down situation, where the crew has to shelter in a dark, shielded area, they'd be running on their internal reserves. Plus, the crew's relationship with their ship would get a lot more personal. They wouldn't just be passengers or operators, they'd be a living, breathing part of the life support system. They'd be super aware that their health directly affects the ship's atmosphere and the ship's health. Its ability to provide light and recycle CO2 directly affects them. This symbiotic relationship could transform the crew's psychological state from feeling isolated in a machine to a sense of belonging within a living, integrated system, a tiny but complete world of their own making. So if we take a step back and look at the big picture, the life of a photosynthesizing astronaut would be almost unrecognizable compared to today's space pioneers. The biggest change is really the shift from reliance to resilience. Right now, missions are defined by the tyranny of the rocket equation and the huge volume of supplies we have to send along. But our solar-powered humans, they'd be defined by their self-sufficiency. They'd carry their power source within their own skin, turning the logistical nightmare of deep space travel into something far more manageable. The umbilical cord to Earth, while never totally cut, would be stretched longer and thinner than ever before. The very rhythm of life in space would be totally rewritten. The clock and the mission schedule would take a back seat to the position of the sun. Daily routines would revolve around light exposure, turning work, exercise, and rest into this kind of celestial dance. Spaceships and spacesuits wouldn't just be mechanical shells anymore. They'd become symbiotic extensions of the human body, personal greenhouses and mobile ecosystems designed to channel the life-giving energy of the stars. The human body itself would become a piece of high-tech equipment, a biological tool fine-tuned for survival in the cosmos, blurring the line between astronaut and spaceship. This transformation would completely redefine our place in the universe. We'd no longer be fragile visitors, totally dependent on the technological bubble we bring with us. We'd become native, in a way, to the solar environment. That's a pretty profound leap. It suggests that to truly explore and settle other worlds, we might need to change not just our technology, but ourselves. We'd become a species adapted not just for one planet, but for the space between them, carrying a little piece of Earth's ancient, life-giving chemistry with us wherever we go. The challenges, medical and psychological, would be huge, but the rewards are just as staggering. In the end, the ability to photosynthesize in space would mean more than just a clever solution to a logistics problem. It's an inspiring vision of a future where humanity works in harmony with the laws of the cosmos, instead of just fighting against them. It's about a future where we don't just visit space, but actually learn to live there, powered by the same stellar fire that first sparked life on our own world. It's a future where we become children of the sun, in the most literal sense, ready to step out into our solar system not as conquerors, but as true inhabitants. And honestly, that's a truly brilliant thought.